Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics 2. In this lecture, we will discuss today what is the separable variable method for the first order ordinary differential equation. Here, before starting this topic, we will discuss the order and degree of the differential equation. Here, as we know that, what is the order of the differential equation? The order of the differential equation is the highest order derivative which is present in the differential equation is called order of the differential equation. And what is the degree of the differential equation? The degree of the differential equation is the highest power of the highest order derivative which is present in the differential equation. When all the derivatives are free from radical powers and fractional. Let us see some examples of the order and degree of the differential equation. 2xy dy equal to x square plus y square dx be a one differential equation which involves the derivatives. So it can be written as dy by dx equal to x square plus y square upon 2xy. Here left hand side we have only one type of derivative which is dy by dx. It is the first order derivative. So this is the first order differential equation and power of this derivative is 1, so it is first order, first degree, ordinary differential equation. In the next example, I am taking dy by dx equal to x square plus y square upon 3y into dy by dx. Here, right hand side we have a derivatives in the denominator. That means derivative dy by dx have a negative power, that is radical power. So first of all we have to remove it, like dy by dx goes to left hand side. Therefore we have a dy by dx whole square equal to x square plus y square upon 3y. Now on the left hand side we have a first order derivative, so it is a first order differential equation, but derivative's power is 2. So it is first order second degree ordinary differential equation. In the next example, we are taking cube root of d square y by dx square equal to dy by dx whole square. Here left hand side we have a second order derivative and its power is 1 by 3. It's a fractional power, so we have to remove it. So take the cube both sides. Then we have a cube root of d square y by dx square equal to cube of dy by dx square. Now left hand side we can cancel the cube root and cube, then we have a d square y by dx square equal to dy by dx raised to 6. Now we have a second order derivative differential equation and its power is 1, so this is second order first degree ordinary differential equation. So this is the method to find the order and degree of the differential equation. In this case, remember that first of all remove the fractional and radical powers and then identify the order and degree of the differential equation. Let us see separable variable method for the first order first degree ordinary differential equation. Here we have a separable variable. How to apply it? So first of all, f of xy dx plus g of xy dy be a first order first degree differential equation. It can be also written like this: dy by dx equal to p of xy upon q of xy. Now if we can rewrite this differential equation as dy by dx equal to f1x upon f2y or dy by dx equal to f1x into f2y, that means the variables are separated here, then we can apply the separable variable method as follows. If we are taking dy by dx equal to f1x upon f2y, that implies it can be written as f2y dy equal to f1x dx. Here we are taking all the functions of y or all the terms of y on the left hand side and take all terms of x on the right hand side. That means the separable, we are separating the variable here. Now we are taking the integration both sides. Here we are taking the integration with respect to y on left hand side and integration with respect to x on right hand side. After taking the integration, if we integrate the functions, then we get capital Fy equal to capital Gx plus c. Here capital Fy is a integration of left hand side and capital Gx is a integration of right hand side. So finally capital F of y equal to Gx, capital Gx plus c be a general solution of our differential equation. Let us see some examples related to this topic, that is x square dx plus sin y dy equal to 0. This is a very simple example. Here we can rewrite this differential equation as x square dx equal to minus sin y dy. In this case, we have already all the variables of x on the left hand side and all the functions of y on the right hand side. That means already variables are separated. So directly we are integrate both sides. We are integrate with respect to x on left hand side and integration with respect to y on right hand side. After taking the integration, we get integration of x square dx equal to integration of minus sin y dy. Now integration of x square is x cube by 3 equal to integration of minus sin y is cos y. As a constant, arbitrary constant, we are taking the c by 3. So finally we get x cube by 3 equal to cos y plus c by 3. Here we can also take arbitrary constant only c. But to balance the equation, we are taking here c by 3. Now multiply all the equation by c. Then we get x cube equal to 3 cos y plus c, which is our general solution of the given differential equation. Here c is arbitrary constant. Remember that our equation is first order, first degree differential equation. So in the general solution we have only one arbitrary constant. In the next example, we are taking the 2xy dx minus x square dy equal to 0. Here we can rewrite this equation like 2xy dx equal to x square dy. After taking this, we separate the variables. We are taking the all variables of x on the left hand side and all the variables y on the right hand side. So it can be rewritten as 2x upon x square dx equal to 1 upon y dy. That is also 2 by x dx equal to 1 upon y dy. Now take the integration both sides. We are taking the integration with respect to x left hand side and integration with respect to y right hand side. After taking the integration, we will continue with this step. 2 by x, integration of 2 by x dx equal to integration of 1 upon y dy. As we know that integration of 1 upon x is log x, so we have a 2 common outside, then we get 2 ln x equal to 2 ln y plus ln c. Here ln c is arbitrary constant, so we can rewrite this line as ln x square minus ln y equal to ln c. Then we can rewrite as ln x square by y equal to ln c. That implies after removing we have a x square by y. After removing the log we have a x square by y equal to c. That means x square equal to yc be a general solution of our differential equation. In the third example, we are taking dy by dx equal to sin x plus y. Here we cannot easily remove the x and y, or we cannot separate the x and y. So we are taking here x plus y equal to u. So we have a du by dx equal to 1 plus dy by dx. That implies dy by dx equal to du by dx minus 1. Therefore, we can put dy by dx equal to du by dx minus 1 in the differential equation. Dy by dx equal to sin x plus y. After putting the value of dy by dx, we get du by dx minus 1 equal to sin u. We are putting x plus y equal to u in the differential equation. Then we get du by dx equal to 1 plus sin u. Now we continue with this step, du by dx equal to 1 plus sin u. Now we convert all the functions of u on left hand side, because we have a du on left hand side. Therefore, it can be rewritten as 1 upon 1 plus sin u du equal to 1 dx. Taking the integration both sides with respect to u on left hand side and with respect to x on right hand side, we get integration of 1 upon 1 plus sin u du equal to integration of 1 dx. Now to integrate on left hand side, we are taking the conjugate of 1 upon 1 plus sin u, that is integration of 1 upon 1 plus sin u equal into 1 minus sin u upon 1 minus sin u du equal to integration of 1 dx. Now we will continue with this step, and then we get integration of 1 minus sin u upon 1 minus sin square u du equal to integration of 1 dx on right hand side. Now we know that 1 minus sin square u is cos square u, so we get integration 1 minus sin u upon cos square u du equal to 1 integration of 1 dx. Now we separate the cos square, then we have integration 1 upon cos square u minus sin u upon cos square u du equal to 1 dx. Then we will continue with this step, integration 1 upon cos square u, which is sec square u, minus sin u upon cos u, that is tan u, into 1 upon cos u, that is sec u. So we get integration of sec square u minus sec u tan u du equal to integration of 1 dx. As we know that sec square u is a derivative of tan u and sec u tan u is a derivative of sec u. So after simplifying, we get integration of sec square u is in tan u minus integration of sec u tan u is sec u equal to right hand side we have a x plus c, because integration of 1 dx is x plus c. Now we have a solution tan u minus sec u equal to x plus c, where c is an arbitrary constant, and this is our general solution in terms of u and x. We have to find the general solution in terms of x and y. So we replace u equal to x plus y, which is already we assumed. Then our general solution will be tan x plus y minus sec x plus y equal to x plus c, which is our general solution of differential equation dy by dx equal to sin x plus y. So this is the method to find the solution of the differential equation by separable variable method. It is applicable when we can easily separate the variables x and y in the division form or multiplication form. After this topic, we will continue same method for the homogeneous differential equation in the next lecture. So here separable variable method for first order, first degree differential equation. In the next lecture, we will discuss the same method, separable variable method for the homogeneous differential equation. Thank you very much for watching.